Hey, hi all. Thank you for the introduction. And let's dive right in. So at this point, you already know everything about ray tracing and uBVHs, but let me do my introduction anyway. You have a scene. This is typically represented by triangles, and you have a bunch of rays you would like to trace. And immediately, you can see this is like some O and square territory, which can get really expensive with many rays and many triangles. So luckily, we can build an acceleration structure such as bounding volume hierarchy. And typically, the traditional bounding volume hierarchy has some leaf nodes. They reference the geometry, the triangles, and some interior nodes that are typically associated with the bounding volume. And most commonly, it is an axis line bounding volume. And this leads to a following traversal pipeline. So for a given ray, you start at the top of the tree, and you intersect with the internal nodes. You fetch their data, intersect, and repeat this process until you reach a leaf node. And in the leaf node, the same actually can happen. You loop over the triangles referenced by the leaf node, and you do this process until you exhaust all valid paths for a given ray in the bounding volume hierarchy. And in the end, you either have or don't have an intersection. And because we want to do this fast, we do this in parallel. But there's a catch with bounding volume hierarchies and ray tracing, and that the algorithm can or is not particularly coherent on average. So often, some lanes are computing and other lanes have to wait until the end of the computation. And similar thing can obviously happen in the bottom loop. And in the end, when the lanes are finished, you maybe have some results, you maybe don't have some results, and you can continue again until all all rays are resolved. And there are tricks how to improve this. Obviously, over the years they were explored, but in general, this problem is inherent to the representation because you have two-stage traversal for two-stage intersection test with the bounding volume hierarchy and with the geometry. And maybe it would be beneficial to introduce a fused kind of hierarchy when the bounding volume and the triangles are represented in the same way. And for this hypothetical hierarchy, at this point, the new intersection algorithm could look like something like this. So for a given array, you fetch the node, you intersect the node, you don't care that much whether it's a triangle or an interior node. You repeat the process again until you exhaust all valid paths for the array, and in the end, you maybe have or don't have an intersection. And when we compare it to the previous traversal loop, it's quite a bit simpler. So the intersection unit or tests are fused, and also the cycles are fused to a single loop. But the question is how to actually get to such hierarchy, because what you would require is a structure that is efficient enough to serve as a bounding proxy for the hierarchy, but also flexible enough to actually represent the triangles. And over the past few years, there's been some more exploration into tau binding volumes for ray tracing, and you actually today heard about most of them. So in 23, Bittner et al. Showed us a way how to construct the uBB hierarchy. A year ago, we introduced the way how to construct the KDOP hierarchy. And just a few weeks ago at the Eurographics, I presented our work on skewed-oriented bounding boxes and their hierarchies. And today, you heard from Michael Kern and colleagues about the revisit of topic of OBBs. And during our work on SOBBs, we actually realized that they might actually fulfill the requirements I mentioned, and might represent the triangles and the bounding volumes at the same time. So what actually is this SOBB, or skewed-oriented bounding box? Geometrically, it is a parallelepiped, and it has an arbitrary orientation of its basis vectors, which would be formed by its axis. So, and the main point why they are skewed is that they are actually skewed against the canonical orthogonal basis. And important thing here to realize or to internalize is that you can represent these boxes in terms of their edges, But you can also think of them in terms of an intersection of infinite slabs in space. This is often used, and it is still true and valid for SOBBs. And why this is important is because that's the way we represent the SOBBs in the previous work. So what I mean by that is that we represent them by a triplet of slabs, or 3 slabs. And one slab can be defined by a normal and 2 projection points over this normal. And if you wrote this down naively, you would end up with 5 floats per slab, and thus 15 floats per SOBB. But you can do a little tiny map transformation. You can rescale the normal, store the offset, and you end up with 12 floats per SOBB. And now that we all understand SOBBs a little better and their representation, let's get to the point. How do we represent the triangle as an SOBB? And let's work backwards from the definition. So the parallelepiped consists of 6 faces, and these are parallelograms. And the parallelogram consists actually of 2 congruent triangles. So here is the triangle, and trivially enough, we can represent the triangle on the face of an SOBB. But this is not the complicated part, because now we have the SOBB, there is a triangle there on its front face, but how do we compute an intersection with such triangle? And to understand this, or key to understanding this, is actually the slab-based representation I introduced previously. So originally, what we did this transformation just to save a float per slab. And later, we realized what it actually does. And what it actually does, the transformation, is that it scales the space in the direction of the normal in such a way that the slab occupies the area between 0 and 1 in a given in this new space. So when you have a triplet of such slabs and they intersect to form the SOBB, you actually introduce a new relative coordinate space, uVW, where the SOBB lies between 0s and 1s on each respective axis. And maybe now you ask why the weird angles, and you have to remember they are associated with the slabs and not with the edges of the SOBB. So to understand this a little better, let's stay in 2D and take at the front face of the SOBB. So you have slab U and slab V. Their intersection clearly forms a parallelogram, in this case a front face. They have these coordinates in this relative space, and also the triangle we are interested in is present in this space and have these coordinates. So what we can do now is we take an intersection point with the SOBB, computed in a way we shown in previous paper, and we can project it to this new relative space. And the test is exceptionally simple then. And this also silently implies that the W coordinate for the front to back slab is 0, so we remain on the front face. And maybe some of you realize there's a bit of a free lunch there because you directly or easily can compute also barycentric coordinates from this representation. And if we go one step further in this direction, we realize that we actually can represent pair of triangles as SOBBs as a form of compression. So the most obvious pair you can represent is this congruent triangle pair that form a parallelogram. This is not super common in scenes, as you can imagine, but it happens. And in this relative space, the intersection test is really similar to the previous one. You either belong to one or to the other triangle, and we still remain on the front face. And more interestingly, we can actually enclose or store two or pair of triangles on the SOBB. We can store any arbitrary pair of triangles that share an edge and are not planar, or are not coplanar. We call this configuration a butterfly, because hopefully also to you it resembles a low-poly butterfly. But anyway, you can, in the same fashion, compute the intersection in the relative space. And here you can notice that we no longer stay on the front face, so for the blue triangle, the W coordinate also matters. And with this approach, we can represent the leaf nodes in this way. We have SOBBs, And the internal nodes are also SOBBs built in a fashion we introduced in previous work. So let's revisit the traversal loop now. For a given array, we fetch the SOBB data, we intersect the SOBB. In case it's a triangle, we do a little bit more computation. We compute the inequalities I just introduced to you. We repeat the process until we exhaust all the paths, and in the end, we either have or don't have an intersection. And when we do this in parallel, there is, on the first side, way less potential for stalling or for divergence in the computation. So that was the theory, and how does this behave in practice? The main thing I want to introduce here is that we measure the uBVH in two configurations. Let's say the baseline uBVH when we only use the triangles, so all triangles are represented by their own SOBB, and the so-called extended uBVH where we also use the triangle pairs in form of parallelograms and butterflies. And so let's take a look at the memory consumption. So the memory here represents the hierarchy itself, and also the triangles necessary to compute the computation for all the hierarchies, because it's the only way to make some sense of it. And as you can see, the baseline uBVH is actually quite hungry, but it improves significantly with the introduction of triangle pairs. With the exception of the crown scene, which I will talk briefly now about, this is a direct result, or the memory consumption is direct result of actually finding the pairs in the scene. And this is a thing I actually skipped a bit during the talk, but yeah, in the paper we introduced two algorithms to find the pairs, because obviously you need to find the pairs to use them. This is the one we used in the results. It's actually also plug-based. I didn't want to mention this here, but with regards to the previous presentation. And the baseline BVH is always 1 in this kind of graph, so all the triangles are SOBBs. And the theoretical limit here is the 0.5 line, where when you can actually pair all the triangles in the scene. And as you can see, our algorithm fails or somewhat fails in the crown scene, and this translates to bigger memory consumption for the extended uBVH. Yeah, so in terms of build time, this is actually our biggest hurdle in our implementation. It's rather slow. It's not super slow because we are still on the scale of milliseconds, but it is slower than all compared references. And funnily enough, when you think about it, for the extended uBVH, we actually introduced additional computation step in terms of looking for pairs. But this translates, and this is apparent from the graph, to actually reduction in this end-to-end time, which is represented here, because the actual expensive part is forming the SOBBs, and the less nodes you have in the hierarchy, thanks to the pairs, the faster you actually get in the end. So there was some price to pay, and what we get in return, we measured that this approach is the fastest for secondary traversal, at least in our measurements in comparison to the references I provided to you. Also, this is ordered from the worst to best improvement. So this is the first time we actually achieved a significant or measurable improvement in a scene such as San Miguel when using these tighter bounding volumes, because maybe not so intuitively this scene is actually very well axis aligned, and so axis line bounding boxes work very well there. And as we move to the right in the graph, the scenes are usually less aligned, so the benefit from the tightness of the volume and not just the triangle representation also translates to our uBVH. And obviously the ship scene is an order of magnitude somewhere else, thanks to its structure of the geometry. So, in conclusion, today, I showed you how to represent triangles and triangle pairs as SOBBs. I also showed you how to compute an intersection with these SOBBs to get an intersection with a triangle in this relative uVW space. I showed you how to fuse them in a hierarchy and how this translates to a new or fused traversal loop of this hierarchy. And in the end, I showed you that in our results, it actually also translates to a faster traversal, which we are happy about. Yeah, and I think that would be all from my side. I was quite faster than I expected. I have some extra slides, but maybe, if you have some questions and if there's nothing to do, I will show you some more results. Thank you.
Great presentation, Martin. Could you comment on where you're doing the distance tests for the triangles?
Excuse me, what?
The distance test, right? You have the aperture test with the barycentric coordinates, but you also need to do the distance test, right? The distance from the ray origin to the triangle, or maybe I've missed it.
Yeah, so that's true. I'm thinking of how to best explain this. We don't really care at this point because it's pretty much the same thing we did previously for the SOBBs, and the distance is just there. Well, I think I can't really give you an answer at this moment because I don't want to misrepresent it. But yeah, you're right that obviously we need the distance, but I actually am not sure at this moment how we will compute the distance. But yeah,
let's talk offline.
Yeah.
Thank you.
Hey, sorry.
Okay, it's on. Thank you for the great idea and the talk. I'm wondering if there is any possibility of false hits or cracks where triangles are joining because they live in different coordinate systems?
Yep. Yeah, so this is, I would say, almost obvious question in this kind of work. So basically the question is whether the intersection test is watertight or not. And to be completely honest, we did not really do this investigation. It obviously, or hopefully, can be explored and fixed if there are problems. And I believe there, for sure, will be some introduced, let's say, by the floating point arithmetic. But for the scenes I presented results for, and our setup of parameters, let's say, we didn't really experience any visible artifacts. But if you really construct a scene or a situation, I believe there will be some problems in this fashion.
Also, is the actual triangle data lives somewhere else, or once you are done with a test, that's it? You don't go another level of interaction and test the actual triangle?
No, that's it. Maybe I should, yeah, in the pipeline, maybe I should put more focus in this. Yeah, there is still present only a single data fetch. So we fetch the SOBB, and for the triangle test, we don't need any additional data.
Okay, great.
Oh, I was going to pinch a question. So one advantage of being old, probably one of the very few advantages of being old, could you compare your work with the work by Rubin and Whitted on their sort of like original BVH, where they were using OBBs to try and infer triangles?
Yeah, so I would love to do that, but I'm not that old. Well, that, I mean, not in a bad way. No. No, I'm sorry, but yeah. So just what I meant by that, that I actually was not aware of this work, to be honest. So yeah, well, shame on me, but I can't really compare to that.
No worries, it's so much.
I just have a quick follow-up question. Have you thought of updatable BVHs, and what happens if you need to update the geometry? So do you need to reconstruct The SOBs?
Yeah, most likely if like the triangles themselves change, like due to some deformation, we obviously would need to reconstruct. And if the hierarchy change, you can probably just refit. In the previous work on SOBBs themselves, we did some refit tests, and it behaves actually better than ABBs in that case, so I presume this will translate also to this work.
Okay, thank you.
Probably have time for one more, very quick.
Thanks, Simon. Yeah, Martin, really excellent work. I had a quick question about the results slide where you showed that the memory footprint was very low for the butterfly and the for the mammoth and the hairball. And I was wondering what makes, maybe go back one more slide, in the memory consumption.
This is the memory
consumption.
that's
it. Yeah, yeah. So what makes the let's see, was it that one? No, there was another one. Maybe.
Well, this is also related, maybe.
Yeah, that's the one. Yeah, exactly. So what makes the butterfly configuration so powerful for geometry like the mammoth or the hairball? You're getting very, very good compression.
Yeah, well, it's actually quite simple. It's because there is such kind of geometry there. And we were actually able to find it. So that's the other part. It's actually not that trivial to find such configurations. There are also some precision problems with the coplanar, not coplanar tests and stuff. So it just happens that our, in this case, the block-based algorithm to find such pairs with shared edge was exceptionally successful, and this is both because it aligned with the scene, and also the scene actually contains such configurations often enough.
Oh, okay. So almost more accident than anything.
Well, is it an accident? It just works.
I see. Thanks.
No. So obviously these scenes, we use them as is or as they are. So what we could do is do some pre-computation. We could, let's say, restructure and topologically do some optimizations. So our own algorithm is actually always successful on them. We didn't do that, but maybe in production setting, you actually would do that with your geometry. Yeah.
Thanks.
Or if we can overrun a little. Okay.
Thank you. I'll be quick. Yeah, cool talk. So ART hardware back in the 90s did something a bit similar, or I think your packing of the geometry is more efficient. One of the problems they had was trying to get parallelograms out of the source data. And if you're doing the shared edges, I was wondering whether the input data for that, whether you have any difficulty getting the data together compared to how you were grouping the contents of the bounding volumes in the first place. Basically, can you benefit at all from preconditioning the geometry that's coming in? I'm
not sure if I get the question. Is it related to? Let's repeat it for me one more time. I'm sorry.
So yeah, twofer. So if you've got scene geometry coming in that's typically designed just to be triangles, how easy is it for you to get parallelograms out of it? And if you've got a representation coming in that's designed to fit to an efficient bounding box, is that the same? Can you get at the triangles that you need to in order to pair edges?
So that's a good question. We didn't really explore it that much. For the parallelograms themselves, as you can see right from this graph, they are not that common in these scenes. And yeah, if the scene is actually designed to work great with ABBs, which one can argue the San Miguel scene, for example, is, we were actually able to extract some value with this uBVH and SOBBs, but I'm not sure if it would be the case in all the time. Well, yeah, but who's constructing such great scenes in the end? So maybe that's some additional bonus of this line of work on tight bounding volumes, that you actually don't really need to care that much about the scene then, and cater it towards greater or faster ray tracing.
Okay, can we thank all our speakers one more time?
Thank you.